Hello everybody and welcome to this compact tutorial. We are going to learn how to create a simple smart contract with the compact language. The compact language is the language that we use on Midnight to create smart contracts, and that's the one that you have to learn in order to create decentralized applications on Midnight. We are going to build a very simple contract. That's one of our examples, the bulletin board, where users can post a message in the contract and other users have to wait for the contract to be available to post another message. This contract introduces a lot of concepts that you are going to use when writing smart contracts with Compact. So it's a very good opportunity to learn all the basics that you need to write smart contracts on Midnight. Let's get started. The first thing to do is to tell the compiler which language version or compiler version we want to use for this contract. To do that, we are going to use the pragma version directive. So you just write pragma language version. So it should be greater or equal 0.14.0. This video is recorded in February 2025. So the current language version of Compact is 0.14.0. Next, you want to import the standard library. The standard library in Compact contains a lot of methods and variables that you can use in your contract to make it easier to write it. So you just write import Compact standard library. Now let's start writing the contract. The first thing that we want to do is to have a variable that's going to keep track of the state of the contract. So we can know if the contract is ready to get a new message or if it's already holding a message. We are going to use an enum to represent the state of the contract. We are going to use that enum later in the front end. So we want to export it so we can use it in the application that we are going to create. And then we just write enum, and this enum is going to be called state. And it's going to have two states, vacant or occupied. Next, in your contract, you can have multiple variables that are going to represent the state of the contract. These values are going to be on-chain and they represent the ledger, so the state of the contract. The first one that we're going to create is the one that's going to tell us if the contract is ready to get a new message or if there's already a message in the contract. To represent those values that are going to be on-chain, use the ledger keyword, then the name of the value, and its type. Next, we want to record the message in the contract, so we need to represent it with the value. The same thing, export, ledger, and the message. And the message is going to be of type maybe and string. Maybe is a type that's exported from the standard library, and it can have two different values, none if there is no value, and some with the value that it contains. The value here is going to be an opaque string. Opaque string is a type that means that the string is received from the front end. We also want to keep track of a counter that we are going to increment every time a new message is posted. The counter is of type counter, which is a special type available in Compact that makes it easier to increment or decrement numeric values. To finish, we are going to keep track of the sender of the message. So we are going to record their address as bytes in the smart contract. Ledger poster is the address that posted the current message that's recorded. And that's it. We set up the ledger of the contract. All these values are going to be visible on chain. The next thing that we're going to do is to write a constructor, and the constructor is going to be called when the contract is deployed on chain. So there is a special function called constructor. And now we can set all the values in the ledger. The state is obviously going to be vacant because there's no message yet. The message is going to be set to none. And we are also going to increment the instance. So because the instance is a counter and the counter is a ledger type, we have different methods that are available on this kind of types. And here on the counter type, we have a method called increment that we can call, and we can pass a value, increment the current instance. So when the contract is deployed, by default, the counter is going to be 0, but here we increment it to 1. Now we are going to create a witness. A witness is a function that receives a value from outside the chain. So the value is the private state of the contract, and we can pass it to the contract during its execution. So here it's witness, and that function is going to be the local secret key. So every user who is going to post a message is going to pass their secret key, and we are going to record it in the contract. Now, let's write the first entry point of the contract. Each entry point is going to be a circuit. So circuit is a kind of function that you are going to use in your compact contract. We want to export it to be able to call it from outside the chain. Then we use the circuit keyword. We give it a name. So it's going to be the post circuit that we're going to use to pass a new message. And it takes a parameter, new message, that's going to be of type opaque string. So this means that a user who wants to post a new message is going to call that circuit and pass a string that is going to be opaque, so it's not going to be visible on chain. And this circuit doesn't return anything, so we represent it by this unique type. The first thing that we are going to do is to assert that the state of the contract is vacant. So it's not possible to post a message if there is already a message stored in the contract. We are going to use the assert function and make sure that the state is equal to state.vacant. And if not, we can return the string attempting to post to an occupied board. Next, we want to save the address of the poster. In order to do that, we are going to call the local secret key. So that means that the user who is posting a new message is passing some bytes that represent their secret key. We are going to generate a hash from that secret key by using a function called public key that we are going to write. This function is going to take the bytes that the user sent and the current instance of the contract. However, the instance is a counter and we want to cast it to bytes in order to be able to hash it properly. At the moment in Compact, it's not possible to cast a counter directly into bytes. So we have to cast it first to a field value and then cast it to bytes. Once this is done, the bytes that we are going to save in state of the contract are going to be visible. However, we are using a witness, and the goal of a witness is to keep the private state of the user secret. Here in Compact, you have to tell the compiler that you are aware that the value that you are passing is going to be exposed. In order to do that, you have to wrap that value in a disclose function, and that's it. Now let's write the public key function. So it's secret public key. So it takes the secret key, which is of type bytes 32, and it also takes the instance that we casted into bytes. And it's going to return bytes. Now we can return directly that value, and we're going to use another function that's imported from the standard library, which is persistent hash. So it's going to hash bytes. We are going to pass a vector of 3 values, which are bytes. The first value is going to be some bytes that we are going to hash from string using first pad function. We need a hash of 32 bytes, and we will use this string. The second one is the instance, and the last one is the secret key. Good, so now we have this function that we are going to use to save the hash of the address of the poster. Now we are going to save the message that was posted into the message field of the ledger. We're going to use the sum function that's exported from the standard library. We have to write the type of value that we are saving here. And we can just put new message. Now that all of that is done, we can change the state of the contract to occupied. And that's it. That's the post entry point of the contract that makes sure that there's no message saved in the contract, that records a hash of the address of the poster, that also records the message that is sent to the entry point. And at the end of the execution, the state is switched to occupied. Now let's see what happens when a user wants to take down a message. As a rule for this contract, only the user that posted the message is allowed to remove it and reset the state of the contract. So we are going to create a new circuit. It's called takedown. That doesn't take any argument, and that's going to return the message that was saved in the contract. The first thing to do is to make sure that there is a message to take down in the contract. So we can write an assert function to assert that the state is occupied. Otherwise, we are going to return an error with the following message: attempted to take down post from an empty board. After that, we have to make sure that the user calling the takedown entry point is the one that posted the message that's currently saved in the contract. So we also use the assert function. And then we go through the same steps to hash the bytes that it provides through the witness to create a hash that we can compare to the one that is saved in the poster value. After that's checked and everything is okay, we are going to save the value of the current message into a variable called former message so we can return it at the end of the execution of the entry point. Now we can switch the state to vacant. We can increment the instance to the next value. We need to reset the message to none. And now that everything is set up to receive a new message, we can return the former message. Now that everything is done, we can try to compile the contract and see if everything works. In order to compile it, you must have the compact compiler installed on your computer, following the steps that are in the documentation. After that, you just have to call the compiler. So we are going to use skip zk. Just to check the syntax of the contract, you don't need to generate the zero knowledge proofs. So we're just going to skip it for now. And then the name of the contract, so contract.compact. Then we have a folder called output where we are going to save all the files that are generated at this step. Now, if everything works properly, it should compile. Here, the error message is pretty clear. I forgot the semicolon after the Pragma version. So I can save it and I can try it again. And here we have another error. So these errors are very good to show you how good the error messages are in Compact. Where the error is here, where I put equal. And now it compiled properly. And you can see in the output folder, we have a lot of folders and files that indicate that everything was compiled properly. So I hope you learned in this video how to create a smart contract in Compact. And you can see that the syntax is very close to TypeScript. So the learning curve is very small, and you can start very quickly writing contracts for the Midnight Network. Thank you very much for listening, and see you in the next one.